We talked about how to do problems involving the average atomic mass of an element. Let me back up here real quick and show you that formula again. Whoops. This is the idea. You take the percent abundance, but express it as a decimal, not a percentage. So 69.09% becomes 0.6909. You divide by 100, right? And you multiply that times the mass of that element, that isotope. And then you add the fraction of the other one times its mass. So I take 30.91, I make it 0.3091, and I multiply by this. I add them together. This is a weighted average, so there's no need to divide by 2. The weighting is this percent here. And then you add them together and you're done. So let's do, I think I was going to do, didn't like that one. I was going to do, gosh, where'd it go? I was going to do this one, bromine. So we should be able to do problems like this. Bromine has 2 naturally occurring isotopes, bromine 79 and bromine 81, and has an atomic mass of 79.904. The mass of bromine 81 is 80.9163. Its natural abundance is 49.31%. What's the mass and natural abundance of Br 79? Okay, scratch that because that's more advanced than I wanted to do first. Sorry about that. Let's do this one. Calculate the mass of silicon using the following data for the percent natural abundance and mass of each isotope. And they're giving us percents and masses. So we need to take these percentages and convert them into decimals. We're dividing by 100. So 92.23% divided by 100 gives us 0.9223. And we're going to do that for all of those percentages. There's 3 of them in this one. So I'm going to take this percent converted to a decimal and multiply by the mass of that isotope, which is given right there, 27.9769 AMUs. And then I'm going to add the percent of the second one. When this is divided by 100, it's 0.04, not 0.4, 0.0467 times the mass of that one, 28.9765. Oh, left off the unit, AMU. Plus the last one, 3.1% is 0.0310 times the mass of that one, and then we just have to punch all those numbers into our calculator. 0.9223 times 27.9769 plus 0.0467 times 28.9765 plus 0.0310 times 29.9738 equals. And my calculator says 28.085485522. It's telling us to report the mass to 2 decimal places. If we work it out with the significant figures, that ends up to be correct. So we're going to report the answer is 28.09 atomic mass units. Any questions? This is the straightforward version of these problems. Everybody okay with that? Okay, now let's do one that's a little more interesting. Let's do this one. Naturally occurring lithium has two isotopes. Lithium-6 with a mass of 6.0151 AMUs and lithium-7 with a mass of 7.0160 AMUs. Determine the percent abundance of lithium-6. So this has a lot fewer numbers in it, doesn't it? Well, let's kind of map out what we've got here. We've got lithium-6. Yeah, that's, wrong buttons. Too many buttons. Okay. Lithium-6, and that has a mass of 6.0151 AMUs. And we've got lithium-7 with a mass of 7.0160 AMUs. And those are all the numbers they gave us. They're wanting the percent abundance of lithium-6. The way we solve a problem like this is we're going to have two equations, two unknowns. They don't tell us what the average atomic mass for lithium is, but could we find that somewhere? We could. It's on the periodic table. 6.941. So the average atomic mass for lithium is 6.941 AMUs. We need that. So we're going to have two variables, and we're going to say, let x equal the fraction of lithium-6. That's what we're trying to find the percent abundance. The percent abundance is just the fraction times 100. So if we found the fraction, we'd be good, right? But we don't know what the fraction of the other one is. So we're going to say let y be the fraction of the other one. So x is the fraction of lithium-6, y is the fraction of lithium-7. Thinking about percentages, because that might be easier to think about, if you have two isotopes, what do their percent abundances have to add up to? 100%, right? So the percent of lithium-6 plus the percent of lithium-7 equals 100%. So if the percentages add up to 100, the fractions add up to 1. So that means that x plus y equals 1. The fraction of lithium-6 plus the fraction of lithium-7 equals the whole thing, 1. And then we have our general equation, which was we took the fraction of lithium-6 times its mass. I'll leave the AMUs out for now. And the fraction of lithium-7 times its mass, and that has to add up to the average mass of that element. This is the same equation that we used in the previous example, but now instead of trying to find the average atomic mass, we're trying to find these fractions or percent abundances. So what we do with two equations, two unknowns, if you've forgotten, is we'll solve this one for x, and we'll say, well, if x plus y equals 1, then x must equal 1 minus y. Now I can plug this in I can plug that in for x. Yeah, let's do it that way. It's not the simplest way, but it's going to work just fine. I can plug this in for x, and then I have an equation with one variable, and I can solve that. So here, instead of writing x, I'm going to write what x equals, which is 1 minus y, times 6.0151 plus y times 7.0160, and that's equal to 6.941. We do run into algebra like this in chemistry, and when you're doing problems like this, the more steps you write out, the better. Because when you do things in your head, sometimes funny stuff happens, and funny stuff is usually wrong. So it's better to be safe and write everything down. So now I'm going to simplify this and try to isolate y. So I have to distribute this. So I'm going to get 6.0151 times 1, which is 6.0151, minus 6.0151 times y, plus 7.0160 times y equals 6.941. I can combine these y terms. So 7.016 minus 6.0151 I get minus 1.0009 times y, and that's equal to 6.941. Running out of space, I'll move up to the top of the slide. Now I need to get this on the other side, so I'm going to subtract 6.0151 from both sides. So we've got 6.941 minus 6.0151 equals, so I'm going to just keep going up here at the top. I'm going to end up with minus 1.0009 times y is equal to, no, I'm sorry, that's plus.
I have a question.
Mm-hmm.
Yeah, no, 10. Okay, yeah.
Yeah, that's plus. Sorry. Those minuses are pesky. So I'll get rid of that. It's plus. And this other side is equal to 0.9259. Then I'm going to divide both sides by 1.009. And I'll end up with y equals y equals 0.9251. To get the percent, I just multiply by 100. 92.51% is the percentage of lithium-7. Any questions about the algebra process? That's not, we didn't find the answer to the problem, did we? We found the percentage of the other one. Well, x equals 1 minus y. We found what, I can't see what I'm pointing at. We found what y is. So then x equals 1 minus 0.9251. So x equals 0.0749. And so the answer we're looking for is going to be 7.49%. Lithium-6. This is not a simple problem. None of the individual steps are particularly that difficult, but it's easy to get lost while you're doing it. Any questions? There's like a whole bunch of different variations on this. Yes?
You know how you got 92.51% for lithium-7, right?
Mm-hmm.
For lithium-6, couldn't you just put 100 minus percent minus that percentage?
Yeah, you could do it that way too. It ends up being the same thing. So I went back to this equation that I had made and used 1 minus the fraction, but that's the same as doing 100% minus the percentage. Yeah, very good point. So things to remember are the percentages of the different isotopes have to add up to 100. Sometimes on a more straightforward problem where they're asking you to calculate the average mass, if there's 2 isotopes, they'll only give you 1 percentage. And then to find the other percentage, you just take 100% and subtract the first one, and that gives you the second one. You just plug it into the equation. Any other questions? So that should be enough to make you dangerous on the worksheet.